Okay, let's start with the book, but before we can get to the book, we have to put it in the right context. In other words, Einstein was not only the only person involved with the development of relativity in general, special, and later on general relativity, but he was not the only fellow, but none of those names survive to this day. And it turns out that a lot of these ideas came when he was a kid, when he was not even a teenager in some cases. So I like to synthesize it with this picture here, if you allow me to do that. Okay, 1887, Michelson and Morley, they run their test on ether. They were trying to prove whether the ether existed or not, because a lot of or just every mathematician really in the 19th century believed there was an ether, and they were just trying to show how that ether behaved or what properties it had. And so they ran a test that proved to many mathematicians that there was no ether. Okay, and this shocked a lot of people because there was a fight after that on whether there was an ether or not, right? And even people today say, no, there is an ether, and Michelson and Morley just did their experiment wrong, or got the wrong conclusion, or whatever. But you can see how old Einstein was. He was 8 years old. He was born in 1879. He was 8 years old when Michelson and Morley ran their experiment. Heaviside, in fact, before Heaviside, really, I got to put this fellow up there. I'll put him in there for a second. His name is Waldemar Voigt. Okay, and Voigt came up with this special notation, which we have the new notation these days, which is that little factor there, which is the v squared over c squared. Okay, he was trying to answer the Michelson-Morley experiment, and as far as I could trace it back, he's the first person to come up with this. It's confirmed by two people, at least, in those days. One is Minkowski, who was Einstein's teacher at one point in time, and also by Lorentz. These people confirmed that Voigt was the guy who came up with that equation. And that little v squared over c squared, that factor there, right, that's a very, very important factor because it underpins all of special relativity. Special relativity would not work without that v squared over c squared, and Einstein was not the guy that came up with that. Okay, he came up with that in 1887, again, to answer the Michelson-Morley experiment. Heaviside, the guy who comes up with the length contraction. Fitzgerald and Lorentz later on, right? Both of them working kind of independently. Apparently, Lorentz was not aware of Fitzgerald's complete work, and so today it's called the Lorentz-Fitzgerald or Fitzgerald-Lorentz equation. And they essentially came up with, this time dilation notion, and also of the shortening of sticks and so on. And it's Poincaré, French guy, when Einstein is only 19 years old, he was still in school, right? Who really comes up with the discovery of special relativity. But these fellows, nobody knows them anymore. I mean, if you study some physics out there, you'll find their names. But if you ask the public, go to China, right, and ask a Chinese on the streets, Chinaman, if he knows who Lorentz is or Poincaré, they won't. Ask him about Einstein. Say, oh, Einstein, yeah, I know who he is. Even though it's not part of their culture, he didn't form part of their culture. But all these people went away. Nobody knows them anymore, right? And Einstein took the credit for all their work, even though Einstein came years later and, used their ideas, put them together. So what did Einstein contribute? Why did he become famous? Or why was he, how did he emerge in this world? Well, he's the guy who said there is no ether, allegedly. Allegedly. I'm going to emphasize that. Allegedly said there is no ether. That's what he was arguing for, okay? But not completely, okay? So what is Einstein's ether? It's important to understand, what he was saying here as far as the ether is concerned. And here's a synthesis of what he said in the first 20 years of the 20th century, okay? This is more or less a synthesis of how he saw the ether. And in general, right, how he saw this space-time thingy out there. One can actually speak about a new ether Okay, he's talking about a new ether, but one may not speak of motion in relation to that ether. Special relativity, it took away the last mechanical property of the ether, immobility. Special relativity does not rule out the ether. Why did he have to say that? Because everybody and their mother believed in the ether. And so he was fighting the entire mathematical establishment of those days. You had people like Poincaré and Lorentz. They both believed in the ether. They were trying to accommodate the ether somehow in Michelson-Morley's experiment, in their conclusion. They say, no, there is an ether. We just need to interpret that experiment, those experiments. They did a couple of them. We need to reinterpret those experiments under the ether hypothesis. Okay, and Einstein's saying, look, special relativity does not rule it out, because he had to please the establishment and he wanted to get ahead in his career, right? But then he says, in general relativity, physical properties are attributed to space. Okay, so now he's taking nothing. Space is nothing. There's nothing called space. What is nothing? It's that which has no shape. It's the opposite of something, which is that which has shape. So now we have a definition for something and nothing. Space is nothing. But he gives physical properties to this nothingness, okay? But no substance or state of motion can be attributed to that ether. So it's a something that is not a substance, whatever that is, because a something is a substance. They're both synonyms in physics. It's that which has shape. And space is that which doesn't have shape. Therefore, it doesn't have any properties because it's not a thing. It's not an object. And if you believe otherwise, all we want you to do is to draw it. Show us a picture of space and identify the contrast, whatever gives it contour, okay? The object that's behind space. That's what you got to do, okay? And it says, but no substance or state of motion can be attributed to that ether. So we have this non-substance, which has physical properties, physical being a synonym of substance, right? And he says it doesn't move, right? Because it moves with respect to what? Would have to move as a whole with respect to something else. The ether became four-dimensional. In other words, he's saying that ether and space-time are synonyms. That's what Einstein is saying. But space-time is not part of special relativity. Space-time is part of general relativity. Space-time, special relativity is general relativity without gravity. In other words, it's what the flat earthers like. It's a flat land. Flat land, you cannot fall downwards because there is no downward, there is no gravity. And so what Einstein was saying is, we can't use the ether really in special relativity, even though it does have properties, right? But we absolutely equate it with four-dimensional space-time. And he says the ether of special relativity is still absolute because matter is affected by the properties of the ether. But listen to this. But the ether is not affected by the presence of matter. So we have a one-way touch. The ether touches the thing, but the thing does not touch the ether. And it reminds me of the movie Ghost, where the ghost, he comes in, he does all of these magic tricks. He comes in and out. He can touch things when he wants to, when it helps the movie, the plot of the movie. But otherwise, he can go through things. And here you get some pictures of this ghost. Okay, here it is. Okay, so what Einstein did, create one-way touch. The ghost touches you, but you cannot touch the ghost. That's so weird, you try to touch the ghost, you can't, but the ghost can touch you. And that's kind of magical, and that's what he wanted to say essentially here. He's saying his ether, as far as special relativity is concerned, is one-way touch. So he invented one-way touch, and that's one of the things that, the mathematicians didn't like too much of those days, the establishment, right? And he says that this asymmetry was solved within general relativity. Did he solve it? Well, he says because matter is influenced by the ether just as matter influences the structure of the ether. And he had to do that. Why? Because he's going to say, what are the field equations? The field equations say that when Mercury takes a step forward, it bends space-time. Because it bent space-time now hits back and changes the itinerary of Mercury. That's what he's saying. So yeah, there is a mutual touch. But in special relativity, he says, well, we don't really need it, but space does still have some properties. And he's going to talk about the properties and not about space itself as an object. That's where the cheating comes in, okay? It says, the only similarity of this relativistic ether concept with the classical ether models lies in the presence of physical properties in space. So he's going to give some physical properties to nothing. Space is nothing. Space is that which has no shape, but it's got physical properties. It's not a substance, but it can hit you in the face. That's what he's saying. And says, no substance and no state of motion can be attributed to that new ether. Okay? So we have this strange ether that Einstein proposed, and it turns out no mathematician really bought into it. Nobody paid any attention to Einstein's ether, and it gradually faded away. Mathematicians had no use for the ether because they were going to do everything with abstraction, with mathematics, with equations, with numbers, right? But we reach today, and we have this Nobel Prize winner. His name is Robert Laughlin, and he says, the modern concept of the vacuum of space, right? Confirmed every day by experiment, is a relativistic ether. But we do not call it this because it is taboo. Yeah, they never got rid of the ether. They never were able to explain what's out there. And they use all these different terms like virtual particles. Here's one example, virtual particles, right? And they have all these particles that are out there, and they live only for a split second in our world to make the equations come out right. And they immediately disappear. Then they are unmeasurable, right? And here this is how they illustrate them, okay? And so you have all these virtual particles, and that's the ether. But they don't call it that because it's taboo. And what is space-time? Well, space-time, again, is also an ether. And you say, what do you mean it's an ether? Yeah, because space-time is defined, or better yet, let's define it in reverse. An event is defined as a point in space-time. That means space-time is made of all these points, all these events that make up space-time. So it's a circular argument, Events make up space-time. What is space-time? A bunch of events. Okay, that's what it is. It's a circular definition, a notion. And what are all these points? Well, particles. And what are all these particles? The background, the background radiation, bunch of particles in the background. It's an ether. It's an ether theory, but they're not going to say that. But Einstein said it. Is ether with this four-dimensional. And of course, mathematicians today don't want to relate the word ether with their four-dimensional space-time. It's taboo, okay? So keep that in mind. But when you give a physical interpretation, you got to have some kind of background there, and that's where the problem comes in. That's when they say, well, that's ontology, that's belief, that's philosophy, metaphysics, who knows what. Okay, so what happened was that something was happening during the days that Einstein was growing up. And that's in 1905, he makes his annus mirabilis, call it the anus mirabilis. He came up with 4 papers, and 2 of those are of some significance. One he won the Nobel Prize for, which is the photoelectric effect. The other one is the one that gives rise to special relativity, which he kind of borrowed from Poincaré, okay, the French guy. Okay, so what's the issue? The issue is that you've got World War I, 1914, and at the time he separated from his wife, Mileva, a Serbian gal. They had 2 kids. She took the kids with her. By 1919, 5 years later, partly surely because of the war, they finally divorced. So 1919 was a great year for Einstein, or or a significant year, because he got divorced, he got married again with his cousin, and that's when Arthur Eddington blesses his theory, and he becomes a household name around the world, okay? And so 1919, because Einstein had predicted that light curves around massive objects such as the sun, and Arthur Eddington had an expedition, which really was not proposed by him, was proposed by another British guy, but he got the credit for it. He says, hey, I proved Einstein right, and that's when he became a household name. Here you have a couple papers of the age, okay? This is from the Washington Times, okay, of those days, and you can see it's an old paper, 1919, because it costs only 3 cents. What costs 3 cents today? I mean, what? My God. It says, eclipse shows space is limited. Greatest discovery in history. It was a big deal. Sir Oliver Lodge, and he was also a head honcho over there in Great Britain, calls discovery great triumph. And the New York Times, also put a little thing there. It says, lights all askew in the heavens. And essentially proved that Arthur Eddington, with his photographs of the eclipse, showed that light curves around the sun. Okay? Or that's what he thinks he showed, because he was not a very smart individual. And so he just bought into Einstein's theory, and that created somewhat of a problem, because you had especially all these Germans who did not like Jews. People like Leonard, who was a Nobel Prize winner. So was Stark. And Stark was also a Nobel Prize winner, and they hated Jews. And so they began to use this term Jewish physics to anything that came out of Einstein, which later on was propagated to people like Niels Bohr, whose mother was Jewish, and other Jews, because, they studied at universities. They were professors at universities, and they used this against that kind of reasoning. The fact that there is no ether, right? One. And the fact that they're using all these weird explanations to explain regular physics. So they said that's Jewish physics. And some people like Werner Heisenberg, who was not Jewish, was criticized quite a bit. He almost lost his positions also in Germany because he was in favor of Jewish physics. The physics we have today, quantum mechanics and general relativity. Those were considered Jewish physics. But that started in 1920. That's when Leonard, especially Philip Leonard, was somewhat of an important guy in Germany because of his Nobel Prize. And he said, look, this stuff has no place in physics, and so they were resistant to all this stuff. And what happened was Einstein's going to publish his book in 1917. He was still a nobody. He becomes a somebody in 1919, 2 years later, probably a little less, right, because of the months. And that's when Arthur Eddington blesses his theory. And that's when he becomes a household name. His name starts being synonymous with intelligence, and that's where Einstein starts growing. So that's the context that's happening out there. But Einstein at the same time could not fight against the people who were supporting him, because he was proposing that there is no ether, and that was against the belief, the religion of the mathematical establishment at that moment in time. So he had to kind of fit it in there, say, look, appease them, Finlandization, they call it. You have to appease these guys and say, look, there is an ether, but it's really space-time. And that's the way he put it. But they never resolved the issue with four-dimensional space-time or whatever. We need to know if there's a physical object called ether out there, if there's a medium called ether or not. Is there a physical object, a medium called space-time or not? And this is what we need to resolve, and they never resolved that. Even to this day, they use it as a physical object, then they say it's a mathematical concept, and they, transfer this mathematical concept and use it as a physical object. And when you question that, they say, well, that's philosophy. You're taking the analogy too literally, and we have to answer how the Earth doesn't fly out of the solar system. Why does the moon get out of the solar system? And they say, well, it's a warp space. Well, that's a physical interpretation. Yeah, we're trying to interpret our equations, but we don't understand Father Universe, and we don't have to speak the same language as Father Universe. But the language of Father Universe is math. We understand the math, and this is the best we can do to translate that math into regular language. And that's the situation today. Okay, and so we have what happened was, Einstein replaced Newton, partly because of an issue of precision, of accuracy. They say that Einstein's equation is more accurate than Newton's. It could explain Mercury's perihelion a little better, just a tiny bit, but that wasn't really the reason. The real underlying reason was that Einstein provided a different physical interpretation to gravity than Newton. Newton essentially said, look, there are particles. He was a particle man. But I mean a real particle, corpuscles, not quantum particles, okay? He was thinking in particles. He was thinking really in terms of what we call gravitons today. And he said, look, the sun attracts the earth, and he was thinking of particles, but he couldn't make them work because you can't attract with particles. And so he says, I have no hypothesis. Fingo non hypothesis, he said in Latin. He had no way of explaining that. And Einstein, and nobody had until Einstein came along. Einstein said, no, because there are no particles. There is not a force. What you have is the bending of space-time. Gravity is geometry. And what you have is the bending of space-time, and the Earth rolls around the sun and the moon around the Earth because space-time is warped. And that's a mathematical it's a physical interpretation of the mathematics. That's what they interpret, that what is being bent is space-time. You have to assign physical properties to this abstraction, this mathematical abstraction. And when you say, well, that's irrational, they say, well, you're taking the analogy too literally. Or we don't do that kind of work anyway. We're trying to explain it as best we can, what our equations mean to us, and we're trying to give that to the public. And so if we have to illustrate it, that's what they illustrate. Okay, so that's the situation. The situation is either we go with Newton or we go with Einstein. And part of the problem here is that in the case of Einstein, his theory doesn't work. Okay, it really doesn't work. They never tell you that it doesn't work, but it doesn't work. Here, let me give you a couple scenarios. One is a rocket in space, right? And it violates Newton's third law. Okay, here it is. And, Newton's third law of motion says for every action there is an equal and opposite reaction. When a rocket goes through space, right, it doesn't push against space. A lot of flat earthers don't understand that. And it takes a long time to educate them. Anyways, a propellant moves backwards, right? And it automatically gives an impulse to the rocket going forward. So there is no push against space. So Newton's third law of motion, right, shows that that space is nothing because you're not pushing against space. I mean, it would be much easier for the people at NASA, for example. When the rocket leaves the Earth, it pushes against the ground. No problem. Everybody understands that. It pushes against the ground, goes upward, right? But in space, it doesn't push against the anything. The thrusters simply push outwards, and by pushing outwards, the rocket moves forward. Okay, that's how a rocket works in space. And it works with Newton's third law, and that violates Einstein's special space-time. Why? Because if space-time were a physical object, right, you could push against space-time and move forward. You wouldn't have to use Newton's third law. Okay, that's the first problem. The second problem is this one, okay, and that's a violation of Newton's first law, and that is that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. What does that mean? It means that here you have these rockets, and the people in NASA, they don't factor that rocket is moving through molasses or through an ocean or through air. No, it's moving through nothing. Because if they had to factor that there's resistance from some kind of medium called space-time, where you have this molasses, this water, whatever medium you want to think of, this fluid out there, ether, right? Then it would have friction. And, they don't calculate that. They don't factor that when they send a rocket out into space. So the rocket not only violates Newton's first law, but also third law, right? Both laws are violated because, in a sense, that it shows that there is no space-time, because you don't push against space-time, and space-time doesn't cause friction on your spaceship, meaning that, it travels in a straight line like if there was nothing there, which is exactly what is out there. Nothing. That's what space is. That's the region between the Earth and the Moon. It's called nothing. Okay? Nothing is that which has no shape, and it has no physical properties. But Einstein had to put some in there. Okay, so here's one fellow, and he writes the following. It says, I have an analog with boats throwing balls to each other and transferring momentum for repulsion and boomerangs for attraction. So he's going to explain Newton's force law using these notions. And if Newton would have found out about this, maybe he could have challenged Einstein if he came around, right? Saying, no, I do have a mechanism. I'm sorry, I thought I had none, but I do. And this enlightens Newton, right? He says, momentum conservation directly for the repulsive, angular momentum conservation in the attractive. As all analogs, it should not be stressed too much. And yeah, you have to really stretch his interpretation, and I'm going to illustrate that here in a second. Here's his boomerang theory compared to his repulsive one. Repulsive one we all understand, with particles, hitting against each other, pushing each other away. The boomerang one is the one that's very interesting. And here it is. Okay, when the pitcher throws a ball, the pitchers move backwards, right? So you throw a ball, or you throw something, for example, heavy, right, forward, you move backwards, right? We all understand that. And the person catching also moves backward because, you're receiving this mass, this rock, this ball, whatever, and you're pushed backwards. So both persons are pushed away from each other. We all understand repulsion. In fact, all you need to do is throw a ball against another ball. You'll see that they'll bounce away. But look at the boomerang theory. Throws the boomerang, and because you throw, you move backwards. No problem there. So far, so good. But the boomerang goes around and pushes the other person backwards. So that's a boomerang theory, okay? If Newton only would have known all that, he could have challenged Einstein. So, now you know the boomerang theory. And here you have the typical one that they use out there. Again, it's beyond comprehension. It's known as negative momentum. I use the quarks here and the gluons, but it can work for gravity as well. If you are talking about two objects, the quarks being two objects, mass, right? And you have something in between them, a little particle that's going back and forth. One shoots the particle at the other object. How does it attract it? That's the question. And they call it negative momentum. Why? Because all you have to do in math is put a negative sign in front of momentum, the little p, right? And suddenly you have attraction. So mathematically, yes, it can be done. Or like we used to say in engineering, you can, with math, you can prove that an elephant dances upon a pin. And that's more or less the situation there. Yeah, you can prove anything with that. Okay, because of Newton's theory, right, of particles and his mass divided by distance squared, right, if the sun were to disappear, right, the Earth would be flying out instantly. There would be no time delay. Sun disappears, the magician comes, makes the sun disappear. Our Earth would go flying out immediately because of the mass distance squared equation, right? So it would look something like this. May not start at the beginning. Let's see. Okay, here it goes. Here's the sun, right? Now we're going to make the sun disappear, okay? And look what happens to the Earth that's rolling around there. Here it comes. Blip. There he goes. You can see what happens to the Earth. It goes flying out of the solar system immediately, okay? So the Earth would receive the message instantaneously. That's what I'm showing there, okay? And here is Einstein's version, okay? And again, in this case, it takes 8 minutes, according to Einstein, because the speed of light is 300,000 kilometers per second, and nothing can travel faster than the speed of light, including gravity. That means that if the sun were to disappear, we would not find out about that until 8 minutes later, when both light and gravity arrives at our light arrives at our eyes, and gravity comes at the same time as a feeling. We feel that suddenly we lost gravity. Okay, here it is. Okay, here's the Earth going around the sun, and suddenly, the Earth, the sun disappeared there. Here, you'll see it from the beginning in a second here. It's a GIF. So here's the Earth going around the sun, and it disappears. And so what does the Earth do? Well, it goes flying out 8 minutes later, okay? Because that's how fast light is. It cannot move instantaneously. So they have this idea that, the light and gravity both travel at the same speed, okay? Which is total nonsense because of what I said earlier, and that is that weight is location specific. It's a static concept. What does that mean in this context here? It means that you have weight for a given location in space, okay? So it doesn't matter where you are around the Earth, you already have weight, whether you put yourself on a scale or not. We don't care about measurement here, okay? You already have weight. And at different locations, location being a static concept, the astronaut already has weight. And if we have weight with respect to the Earth, and likewise the Earth has weight with respect to the sun. If the sun were to disappear, we're missing one of the masses. Mass, distance squared. You erase one of the masses, well, now you don't have any gravity, because that's what it was, a separation between two objects. You make one object disappear, the other one has no mass. Okay, if we removed all the objects in the universe, right? And we only leave the sun and the Earth, and you make the sun disappear, what gravity does the Earth have with respect to what? That's the issue. Okay, you need that mass distance in the denominator. And so, this notion that it takes gravity 8 minutes to reach you when the sun disappears, absolute nonsense, poppycock.